The second half of this section is called the ambiguous case, and our goal is to tackle it, and we'll talk about what the ambiguous case for triangles is, so on and so forth. Before we go on to the ambiguous case, I sort of want to wrap up or summarize what you did yesterday. I'm not sure if you guys noticed or not, but in the last section, you were solving basically the same type of triangle over and over and over again. For example, I'm just going to pull two examples straight from yesterday's homework. So from yesterday's practice, you were asked to solve the triangle given, and one example was like angle A is 50 degrees, angle B is 68 degrees, and side C is 230. We're not going to solve this. You should have solved it yesterday, but I just want to list it and label it out. And heck, I actually want to draw it out too. So in just a random triangle, A, B, C. So what information in this particular problem did they give you? So they gave you angle A, they gave you angle B, and they gave you side C. So I'll just see if I can highlight this, make this thicker here. There we go. So in terms of information that they gave you, these were the pieces of information we were working with, right? So let me go ahead and sort of dash line the pieces that we don't have. So they did not give you angle B, or side B, excuse me. They did not give you side A, and I'll leave angle C unmarked. Now, in geometry terms, you should have talked about, congruence theorems and similarity theorems. So in that vernacular, we would say that this is an angle side angle case. Why? Because they give you an angle, they give you a side, and they give you the immediate adjacent angle. Everything's adjacent to each other, angle side angle. Another example from yesterday's practice was they gave you angle B, for example, 10 degrees. They gave you angle C, for example, 100 degrees. And they gave you side C, say 115. And again, if we were to sort of draw this out, A, B, C, what information did they give you? They gave you angle B, angle C, and side C, which I will bold like this. So everything else, I'll do a dashed line indicating that they did not give it to us. So they did not give us side B, they did not give you side C, or side A, excuse me. Come on. Yeah, thank you. So what type of case do we call this? Well, if we highlight the pieces that were given, they gave us a side, immediately they gave us an angle, and immediately they gave us another angle. So this is a side angle case. So in summary, these were the two cases that you were solving yesterday, so I guess we can make a rule. We can say that if you're solving an angle side angle or a side angle case, law of sines will work. And the reason why they work in these situations is because no matter what, we're always given an angle and opposite side pair. In the side angle case, it's explicit. Angle, opposite side pair. In the angle side angle case, even though they don't give us angle C, we can actually solve for it because 2 out of 3 angles of a triangle, you can always solve for it. And then you have your angle opposite side pair. Well, it turns out that there's actually a third situation that law of sines will work. There's a third triangle setup that will give you an angle opposite side pair. That is the side angle case, right? So there is another setup where law of sines will work. That's the side angle case. Why is that? Well, if I draw it out, what does a side side angle look like? Well, it means, say, we have this angle here, we have the side here, and we have this side here, right? So angle, side, side. I'll let you write out the acronym for yourself. That means we do not know what the side length is. And we can see in this case there is an explicit angle opposite side pair, and thus we can use law of sines. However, there's something peculiar, or something not dangerous, but something we have to keep in mind in this particular case. As you can see in this diagram, this top angle here is not restricted. It's unknown. It can vary. How big is it? How small is it? How wide? How narrow? We don't know. Because that top angle can vary, it has the possibility of swinging this side length out. And based upon how much that side length is, it may swing to a point where we do not have a unique triangle. This is the reason why. Even though this side length here is not given to us, that's why I did a dotted line, this angle was, which means this side length cannot move. So even if you have an angle, so let's say I give you this angle here, I may not tell you how long these side lengths are, right? It could be very short, it could be very long, but I know for a fact that these two side lengths cannot be moved. They are fixed. So that is sort of like the issue here, that because this side length is fixed in terms of movement, and because this angle is not, this side has the ability to swing out. I think this is a lot easier to see in an animation. So take a look at this guy here. So this is just a little applet to visualize what's going on here. So this is an angle side-side or side-side angle situation. You can see that in this instance, angle 50 degrees is fixed. Side length of B, 11.1 is fixed, and side length of A, 9.4 is fixed. But this top angle here is not, so I am allowed to move this side length however I want. Now, depending on the length of side A, notice I could have this triangle here in this instance, or I could have this triangle here in this instance. But of course, side A could be a particular length such that I could have this triangle here and no other triangles. So that's just my only triangle. Or it could be such that, you know what, no matter how far I swing, it could be way too short to not make a triangle at all. So that quickly sort of rundowns the three possibilities when you run into this side-side angle situation. So that's just to summarize, this situation, the side-side angle situation, presents multiple possibilities. So side-side angle situations have multiple possibilities. The opposite side could be too short, where no matter how you swing it, you'll have no triangles. The opposite side may be such that when you swing it, you'll only have one triangle, right? So this guy right here. I guess I should do this right there. Or it could be such that you have two possible triangles. So as you can see, depending on what the opposite side length is, we have one out of three possibilities. And if the third possibility is having two triangles, we have two sets of final answers. So if I didn't have this fancy computer program, right, if I didn't have this fancy applet to show me how many triangles do I have, the question is naturally, Mr. Vo, how do I know what type of situation we have? Well, there are rules you can memorize, right? If you go into your Google search and look up ambiguous case rules, there are lots of rules to remember. You have no triangles if A is less than the height. You have a right triangle if A is equal to the height, and you have two triangles if A is bigger than the height, but A is less. It's so gosh darn confusing. I don't like memorizing random rules. Let's understand why mathematically the ambiguous case comes up. Recall that the inverse sine function only gives answers in the following quadrants: negative 90 degrees to positive 90 degrees. But there's always a big but in math. We know sine is positive in the first two quadrants. So that's why I sort of made you, I think it was 6.4, that's sort of why I made you solve the simple trig equations in the first two quadrants, because we know that in the world of trigonometry, acute angles and obtuse angles share the same sine values. Sine of 30 degrees is the same as sine of 150 degrees. Sine of 40 degrees is the same thing as sine of 140 degrees, so on and so forth. So because that sine is positive in the first and the second quadrant, when you take an inverse sine of a positive value, you always have to ask yourself, is an answer in the second quadrant possible? So that's how you know. That's sort of like the big idea. Whenever you take an inverse sine to solve for an angle, always check to see if the obtuse angle, that is to say, the angle in quadrant 2, is possible. What does it mean to be possible? Recall that the sum of all the angles in a triangle must be 180 degrees. So if the obtuse angle makes that sum impossible, then you know you only have one solution. So let's go ahead and do an example of the various cases, right? So let's just do an example. Well, I guess I'll spoil it. Let's do an example of the side-side angle situation with one possible solution. Right. So I'm sort of spoiling it for you, but let's pretend we don't know it's one solution. All right. Suppose I ask you to solve the triangle where angle A is 125 degrees, side A is 12.4, and side B is 7.6. So the first thing I would do is I would sketch it out. A, B, C. So they tell me that angle A is 125, side A is 12.4, and side B is 7.6. So hopefully everyone can see that we need to solve for angle B, angle C, and side C. So based upon what we have, hopefully we can see that, hey, we're given an angle opposite side pair, and with the only other information we're given, side B, we need to solve for angle B. So that's what we're going to solve for first. So just set up law of sines as we did yesterday. So sine of angle B over side B is equal to sine of angle 125 over his opposite side. And then you just as yesterday, get B by itself, multiply both sides by 7.6. And then we're going to take the inverse sine of that ugly mess. And if you do that, you are going to get approximately 30.1 degrees. Now, this is what I mean by checking. So here's sort of like the thought here. Our calculator, we got theta is 30.1 degrees. I always have to ask myself, and I got the answer using an inverse sine. I have to ask myself, is it possible for this theta to be in the second quadrant, in quadrant 2? So our calculator gave us 30.1 degrees. If he was in quadrant 2, 30.1 degrees, that means the theta could be 180 minus. So 180 minus 30.1 is 149.9 degrees. Okay. So this is what you should be thinking. If, and this is a big if theta was obtuse, 149.9 degrees, then if I were to add it to the other angle that I already know, 125 degrees, we should know that that is bigger than 180 degrees, which means there isn't enough leftover angles for angle C. So if angle B was 149.9, it is impossible. So this tells me it's not possible. Therefore, only one possible triangle. So instead of memorizing rules, if H was this and R, it's so confusing, just do a quick check. Okay, my calculator, I solved for an angle using inverse sine, 30.1. Quickly, what is this obtuse angle? Subtract it from 180. Is it possible to have another triangle? Yes or no. In this case, it is no. So then you just proceed on with the example as normal. You solve for angle B. That gives us two angles, so I can immediately solve for angle C. I know that angle C is 180 minus the other two angles. So angle C is about 24.9 degrees. And once I have angle C, I can solve for side C using law of sines. So side C over the sine of 24.9 degrees is equal to 12.4 over sine of 125 degrees. As I said yesterday, I try to use given values as much as possible. I don't like using calculated values if I can avoid it. So multiply both sides by the sine of 24.9 degrees. Pop that guy into your calculator and you're going to get about 6.4. So here's an example of an ambiguous case where mathematically, right here, we have shown that there's only one solution. Let's do an example of the side-side angle case with no possible triangle. So suppose I ask you to solve the triangle given angle A is 42 degrees, side A is 70 degrees, side B is 122 degrees. So as always, if I am not given a diagram, I like to draw it out. I'm given angle A, 42 degrees, side A, 70, side B is 122. That tells me I need to solve for angle B, angle C, and side C. So based upon the information they give us an angle opposite side pairs. That means law of sines is unlocked. And based upon the only other information I'm given, I need to solve for angle B. So set it up. Sine of B over his opposite side is equal to sine of A over his opposite side. And then to solve for B, multiply by 122, sine of 42 degrees over 70, and angle B is the inverse sine of that guy. But here's the problem. If I were to take a calculator and try to pop that guy in, it's going to give me an error. Why is that? I mean, looking at our work, I'm pretty confident that we did the math correctly. We correctly multiplied by 122. We correctly took the inverse sign, and I'm pretty confident in my button typing ability, yet I still got an error. Well, let's go this path here. Let's actually do the inside stuff here. So if I were to do 122 sine of 42 degrees all over 70, we get approximately inverse sine of 1.1662. We're putting in a number bigger than 1 inside of a sine function. Recall that the domain of inverse sine has domain of -1 to 1. So we are trying to answer this question. What angle has a sine value of 1.16? That is physically impossible because there aren't any angles. So that's why the calculator threw an error, and that's why we say no possible triangle as our answer. So assuming you didn't mess up pressing buttons, assuming you didn't mess up your math in the intermediate steps, how do you know if you're going to have no triangle situation? The math will tell you. And this is why I love, doing it this way instead of memorizing rules. Is memorizing rules faster? Probably. Right? If you had a photographic memory, you knew all these rules, you would probably answer this question faster. But you know what? Law of science, it's not a long and tedious thing. So I rather just bank on insurance, trust the mathematics to tell you. So let's take a look at the next example. You can probably do process elimination to know what this is about. Example of the side A case with 2 possible triangles. Right. Suppose I asked you to solve the triangle given angle A is 43.1 degrees, side A is 186.2 degrees, and side B is 248.6 degrees. So let's draw it out. A, B, C. Angle A is 43.1 degrees. Side A is 186.2. Side B is 248.6. I'm asked to solve for angle B. I'm asked to solve for angle C and side C. As before, we're sort of forced to solve for angle B given the information, so let's set it up. Sine of angle B over his opposite side of 248.6 equals sine of angle A, 43.1 degrees, over his opposite side, 186.2. Multiply both sides by 248.6. Gives us sine B equals 248.6 sine of 43.1 all over 186.2. And then we take the inverse sine. So if you take the inverse sine, you're going to get about 65.8 degrees. But we took an inverse sine. Anytime you take an inverse sine to solve for an angle, you always have to ask yourself, what about quadrant 2? Is it possible? Well, that means theta could be 180 degrees minus the 65.8 degrees, which is 114.2. Is this possible? You take that possibility, 114.2, and you add it to what they gave you, and you ask yourself, is it bigger or smaller? Well, if you add 114.2 with 43.1, you get 157.3 degrees, which is certainly smaller than 180 degrees. So this is possible. What does that mean? That means we're going to have two sets of answers. So this answer of 65.8 degrees, I'll call it B sub 1. So that's one possible answer. And then you just run through the process as we've done countless times. The only difference is any information that you get using this angle, you just call it subscript 1. So I know that angle C sub 1 is just 180 minus the given angles, 43.1 and 65.8. So angle C sub 1 is 71.1 degrees. And then once I solve for angle C sub 1, you can solve for side C sub 1 using the law of sine. So that's basically the only difference here. Everything else works exactly as we have done it countless of times. Right. So law of sines based upon the triangle that they gave us. So multiply both sides by sine of 71.1 degrees over sine of 43.1 degrees. So C sub 1 is approximately 257.8. So that is one possible triangle. I could have a triangle that has angle A as 43.1, angle B as 65.8 degrees, and angle C at 71.1 degrees with the given side lengths. But since we know that this guy is possible, we actually have to branch off to a separate situation. So angle B sub 2 could be the obtuse angle, 114.2 degrees that we said was possible. That gives us a completely different series of information for angle C sub 2 and side C sub 2 that we have to mark down. So angle C sub 2 is going to be 180 degrees minus the given 43.1 degrees minus the 114.2 that we calculated as possibly being angle B, which gives us 22.7 degrees. And then you have to basically do law of sines again with this new angle. So I'm calling it C sub 2 because we're using information gathered from angle B sub 2. So C sub 2 over sine of 22.7 degrees equals 186.2 over sine of 43.1 degrees. But the motions, the logic, the problem solving is 100% the same. The only thing that really differs are the numbers and the concept that we might have a possible obtuse angle rather than an acute angle. So this is approximately, 105.2. So there we have it. The three possible cases of the ambiguous case. You could have one possible triangle, you could have no possible triangle, or you can have two possible triangles. And it all stems from the fact that in a side-side angle case, depending on the length of that opposite side and how you swing it, you could have no triangles, you could have exactly one triangle, or maybe possible to have actually two triangles. Right? So there we go. That is the ambiguous case. To summarize, in summary, whenever you use the inverse sine function to solve for an angle, always check if the quadrant 2 angle is reasonable. Right? That's the moral of the story moving onwards. Not just in the ambiguous case, but in all cases in your mathematical career, if you take the inverse sine function, just do a quick check for the obtuse angle. I want to do a bonus example, a word problem, because hey, you will have word problems in this section, and I might as well, give you an exemplar to work with. Right? So suppose you have a bird is perched on top of a pole on a steep hill. So you got lots of things going on. You have a bird and a pole and on a hill. An observer is 110 meters downhill from the base of the pole the angle of inclination of the hill is 50 degrees, and the angle between the hill and the line of sight of the observer to the bird is 9 degrees. Find the distance from the observer to the bird. Lots of information going on here. Definitely we're going to have to draw this out. Right. So if you need time to copy down this problem, just pause the video. I'm going to scroll down to give myself some room. So they tell us we have a hill. So here's a hill. And on top of it is a pole. So there's the pole. And on top of that is a bird. There's your bird. They tell us the angle of inclination of the hill is 50 degrees. Now the angle of inclination is the angle of the physical hill. So if this line here is the hill, then that means the angle that the hill makes with the horizontal is 50 degrees. Now I have an observer 110 meters downhill. So here's the hill again. So if I put the observer here, this is 110 meters. What else do they tell me? They tell me that the angle between the hill, which is this bolded line here, and the line of sight from the bird to the observer. So if this point down here is the observer, I draw a line of sight from the observer to the bird. I know that that angle is 9 degrees. I'm going to give myself some room here. So this is 110 meters. I know that this angle here is 9 degrees. Did I use all the information? I used the 110, I used the 50, I used the 90, not 90 degrees, sorry, 9 degrees. There we go. Yep, I've used everything here. So let's go ahead and solve this problem here. I'm going to label what they want me to solve for. So they said find the distance between the observer and the bird. There's that linear distance here. So first thing you want to do is focus on the thing you're asking to solve for and ask yourself or figure out what triangle is it a part of. Well, clearly this guy here is a part of this highlighted triangle. Now, it's not a right triangle, so I can't use SOHCAHTOA. The next thing I'm going to ask myself is, do I have an angle opposite side pair? Well, let's look at the information they gave us. They gave us the 9 degrees, and his opposite side is this guy, which I don't have. They gave us 110, and his opposite angle is this guy here, which I don't have. So this looks like SOHCAHTOA and law of sines doesn't work. How do I do this? Well, here's the idea, and this is a very typical thing to do with trees on the hills, poles on the hills, is what you want to do is extend the object, the hill, the pole, the tree, whatever, down to the horizontal. That forces a right triangle. Now, if you look at the big right triangle here, we should be able to solve pieces of those guys. Because, notice, if I tell you that this is 50 and this is 9, we automatically know that the whole angle here is 59 degrees. Which means, by process of elimination, if I have a right triangle and I know one of the acute angles, the other acute angle must be complementary. So if this angle down here is 59, this angle on top here has to be 90 minus 59, that's 31 degrees. Now I have enough information for the first triangle that I was looking for. So I'm just going to focus on this triangle now. So I'm going to sort of like just blow up that picture there. So I'm only going to look at this part, and this part here. So we have this D that we're looking for. We just said that this is 31 degrees. We said that this is 9 degrees, which means I should be able to solve for this angle, right? Because, 180 degrees minus the other two angles gives us, so what's that? 180 minus 40 is 140 degrees. We also have this as 110 meters. Lo and behold, what do we have? We have an angle opposite side pair. We can use law of sines because we have an angle opposite side pair there. So that is sort of like the trick or the thought process with this particular problem, and we are done here. So we're solving for D over the sine of its opposite angle, 140, equals, the only other information we have is the 110 with the 31. So 110 meters over sine of 31 degrees, multiply both sides by sine of 140. And then you break out your calculator, and you're going to get approximately 137.3 meters. So the bird is about 137.3 meters directly away from the observer. Right. I didn't really have to do any checking. Is this an ambiguous case? No, because we did not use an inverse sine. You only really need to check. You only really have to worry about ambiguous cases if you have a side-side angle situation, or if you don't even want to remember that, is if you are taking an inverse sine. So there you go. So this lesson should be very similar to yesterday's, except check, think. Don't be a mindless robot.